This technical series is presented by Iggy Brigado, Senior Sales Engineer for JPS Interoperability Solutions.
Receiver IP backhaul, particularly with the SNV 12. As you probably already know, we do have a solution that allows us to vote over IP links. And this is a kind of a little close-up of our analog SVM site voter module. And this is an analog module. It supports a single receiver transmit site. And there are 12 of them on the right side of the voter. You can stack 3 of these voters to support up to 36 receiver sites. We can go beyond that by doing multiple tier voting. In essence, that site voter module contains a digital signal processor that measures the spectral noise. We have the delay buffers so we can slow the audio down to match the late arriving audio. And we have gain controls such that we can create seamless handoff between the different receiver sites. So this module has been around for quite a while. Its primary backhaul method is analog 4-wire. Lease line, tie lines, voice grade lines, T1 microwave, but not IP links. So some of our engineering development folks have come up with a solution to vote over IP links. And this is the new SVM3 module. We're currently in alpha and beta testing right now. Hopefully is going to be in production very soon here. And I think Dave mentioned that it is available for sale now. But the SVM3 module is a purely digital module. It's a 3-site module as opposed to the SVM2 is a single-site analog module. This SVM3 module will support 3 remote receiver sites, and this works in conjunction with another module called a QMT-1 module, stands for Quality Measurement and Transport module. This module resides directly at the receiver site, so this alleviates a lot of things. One of the most important things it alleviates is it measures the spectral noise immediately from the receiver site. We don't have to compress the audio through vocoders, lossy vocoders, deliver it to the vocoder in a degraded fashion and misvote. We're going to measure the spectral noise, 2.2 kilohertz in this case, directly at the receiver site. And we can, again, support 3 separate links. The QMT module contains the digital signal processors as well as the digital filters and the faculties to sense the unsquelched nature of the receiver site and measure the spectral noise. The other thing that the QMT-1 module does, it continuously analyzes the network path length, essentially the virtual latency or the fluctuation of the latency. So the way we do this is through what we call a time sync. And the control processor module, the CPM3, within the analog voter, is essentially the brains of the system. It sets the voting criteria. It controls the rest of the modules. But it also delivers what we call a time sync signature to the parent SVM3 digital module, which then in turn distributes the time sync to its subordinate QMT modules out at the receiver sites. So what this essentially does, it aligns every QMT module clock. We just want to reference to the control processor modules. We have an ability to use a network timing protocol, but really, for all intents and purposes, it's really not necessary because we're trying to reference the receiver sites to the master or the parent voter itself. So we're continuously sending these time syncs at a rate that's variable. We recommend every 60 seconds realign the clocks at the QMT module. When the site fully quiets, a couple processes begin occurring. The first thing we do is we begin the measurement of spectral noise at the QMT module, and then we place that information, the quality information, into the ROIP packet, and we deliver the ROIP data to the parent SVM3 module, which we then hopefully vote and deliver to the voting system. The second thing that occurs is each of the ROIP packets not only contains the spectral noise, the correlated audio, the voice that we're interested in, it also contains the time sync signature. Once delivered to the voter, the control processor module looks at all the time sync information being delivered from the subordinate sites and realigns the receive audio delay in not only the SVM3 module, but the SVM2 modules on a dynamic basis. So the time sync is important because that signature is contained in the ROIP data. We don't really care anymore how long the physical or the virtual length of the network is. Latency can change, but we don't care. And we do this, again, without any timing sources. So again, we measure the spectral noise at the receiver site, and we place the time signature or the time sync signature into those packets, which are used to reference at the voter, and we dynamically adjust the receive audio delays of not only the analog SVM2 modules, but the digital SVM3 modules, preventing misvoting.